Okay, so you are going to begin. Are there questions? Okay, so if there are no questions, we'll start. Okay. So let me briefly recall first what we learned last time. So our goal was to calculate the vacuum expectation value of the time ordered product of operators. And the specific theory that we are dealing with is 5 to the 4 field theory, okay, where you have a free Klein-Gordon action, and there is a term which involves 4 files. And what you saw is that this vacuum expectation value is given by the ratio of numerator and denominator. Numerator, I'm going to use the language of Feynman diagrams, but if you don't like Feynman diagrams, you can always think of this as a sum of terms, okay, that you get by following the standard procedure. Okay. But in the language of Feynman diagrams, the numerator is given by Feynman diagrams, whose vertices include n external points. Okay, those correspond to this x1 to xn. Each of these points have one line coming out, okay, because this is phi of x1, phi of x2, and so on. And then m internal points, okay, and each of these internal points have 4 lines coming out. Okay. And this number 4 is associated with the fact that you have a 5 to the 4 interaction. Okay, if you had a phi cube interaction, then each internal line will have 3 lines coming out. And then the rule is that with this, we draw all possible Feynman diagrams. Okay. And then for each such Feynman diagram, we can associate an expression. Okay, we write down the expression and then we add up their contribution. So the expression is given here. Okay. M is the number of internal points. So this 1 over m factorial came because you had an exponential of integral of hi, okay, which we expanded, and mth power contained 1 over m factorial. The same exponential gave this minus I lambda over 4 factorial to the m term, okay, because this accompanies hi. And then you have propagators and combinatoric factors. Okay, so you put all of these together. And at the end, we have to make sure that we integrate over the space-time coordinates of all the internal points. Okay, so this is the final step in evaluating the Feynman diagram. Okay. And then the idea is that you have to calculate all such Feynman diagrams and then add up their contribution. And the rule for the denominator is the same, okay, except that there are no external points. Okay. So rule for the denominator is the same except that n is 0 here, so no external points, so there are only internal points. So to order lambda to the m, we have to work with m internal points, okay, and then again draw all possible Feynman diagrams and evaluate them exactly as for the numerator. And one point to note here is that if we are trying to calculate the result to order lambda to the m, then there are m internal points at most, okay, because both the numerator you have to keep up to order lambda to the m, and the denominator you have to keep up to order lambda to the m. Okay, denominator, let me remind you, starts with 1. Okay, maybe I can go back a little for the denominator factor. Yeah, so this was the denominator factor. Okay. So the first term here is just 1. Okay. M equal to 0 term because none of these integrals are there. Okay. These are all just 1. So the inner product of 0 with 0 is 1. Okay. So the denominator starts with 1, then order lambda square, order lambda cube, and so on. Okay. So when you divide the numerator and denominator and keep terms up to order lambda to the m, okay, we have to deal with diagrams both in the numerator and denominator up to at most m internal points. And that basically means that you have to always calculate a finite number of Feynman diagrams, right? So it's not an infinite amount of calculation. To any order in lambda to the m, any fixed order in lambda, you have a finite number of calculations to do. So are there any questions at this point? Okay.
Hello, sir.
Yes, go ahead, please.
But the series is infinite, right? The exponential factor is sitting inside the
exponential factor. No, the
right.
exponential factor you have expanded out, right?
Yeah.
So it's in the denominator, it's here. This is the full factor. There is no other exponential factor, right?
Hmm. But if we calculate up to order lambda to the power m only, but there will be more terms.
Yeah. But the
Beyond
point
that.
is, in perturbation theory, right? You always calculate up to a given order in lambda.
Yeah.
So you are doing perturbation theory in lambda.
Yeah.
Think of ordinary perturbation theory in quantum mechanics. Right? When you calculate the shift in the ground state energy, right?
Yeah.
You don't calculate the result to all orders in perturbation. Because then you got to solve the theory exactly, right? You solve it, you calculate the shift in the ground state energy to a given order in lambda. And it's the same kind of calculation you are doing here, right? You have lambda, which you have saying is a small parameter. And we calculate this Green's function up to a given order in lambda.
But sir, it is also true for any arbitrary lambda, right? You have said in the first.
Well, up to this point, it was true up to arbitrary lambda when it was in the exponent, right? Well, see this, if you are willing to sum to all orders in M, then it's true for arbitrary lambda, right? Or in this form, for example, it's true for arbitrary lambda. From here onwards, we organize this in such a way that is suitable for making an expansion in powers of lambda. Because each HI is a factor of lambda, right?
Yes.
If you have to calculate the result exactly in lambda, then this expansion will not be very helpful. This expansion is helpful because you want to calculate up to a given order in lambda.
Okay.
Is this point clear?
Yes.
So this one, if you could calculate exactly, then you don't need perturbation expansion, right? This is the exact expression. Any other question? Now, I should also add that what we are doing here is also valid in quantum mechanics. And I mean, in fact, I'll probably set it up as a homework problem. That imagine that you had harmonic oscillator, okay, which you know how to solve. But we make it an anharmonic oscillator, okay, which means that we add to the harmonic oscillator Hamiltonian a term like lambda over 4 factorial x to q to the 4, okay, where q is the coordinate. That can be thought of as a 0 plus 1 dimensional quantum field theory, right? A quantum field theory with one time and 0 space dimensions. And whatever you have done here, okay, is applicable in that situation as well. So if you want to calculate the time order, the vacuum expectation value of the time order product of Qs, for example, in an anharmonic oscillator, you can do perturbation expansion exactly by following the same procedure. So what you are doing, of course, is valid in quantum field theory, but it's not specific to quantum field theory. So this is a general procedure for doing time order perturbation theory, the time-dependent perturbation theory. Are there questions? Okay, so let me describe some example. This is what we started yesterday, but let me go through it in a little more detail. Okay, so the particular example that we considered was n equal to 4, m equal to 1. Okay, so we are calculating the 4-point function and order lambda contribution to the 4-point function. Okay. So the rule is that you first draw these 4 external points, okay, each with a short line coming out, one short line coming out because of the fact that each external line has only one phi. And then you have one internal vertex because you have m equal to 1, okay, which has 4 lines coming out. And the rules for constructing Feynman diagram is that you just connect these lines in all possible ways. And for each such possible way, there is a Feynman diagram. So you start connecting lines, and the claim is that the kind of Feynman diagrams that you will get by making arbitrary connection must be of one of these 3 classes. So this one comes when you take 1, join to one of the lines here, take 2, join to one of the lines here, take 3, join to one of the lines here, and take 4, join to one of the lines here. This one, for example, comes when 1 and 2 are joined together, Okay. And then 3 is joined to one line here, 4 is joined to one line here, and the two leftover lines are joined to each other, right? That's what this loop represents. This one, on the other hand, corresponds to 1 connected to 2, 3 connected to 4, and then 2 lines here connected to each other, 2 other lines connected to each other. And here I should also say that these are not the only diagrams. You also have this, in fact, corresponds to, there are 6 diagrams of this kind, right? Because you could have replaced 1 2 by 1 3 or 1 4 or 2 3 or 2 4 or 3 4, right? That's 6 possibilities. Then the rest is fixed. Here there are 3 possibilities, right? Either 1 2 3 4 or 1 3 2 4 or 1 4 2 3. Okay, so there are 3 diagrams of this kind. Okay, so those have to be counted as separate diagrams because their expressions are going to be different. So is this clear how to construct these diagrams? Okay. Now, one thing I should say that if you just start drawing diagrams, okay, you may never be sure that you have actually found all the diagrams, right? That you have drawn all the possible diagrams. Because how do you know that you have not missed out something, right? So I'll just discuss in the next slide, okay, how you can possibly decide that you have not missed anything. Okay, if you think that you have drawn all the diagrams, that is a way to check if you have actually drawn all the diagrams. Okay, so let me then consider that example in more detail. So we have these 3 classes of diagrams. Okay, so let's evaluate this. So here to evaluate this, so let's call this point x. Okay, this is x1, x2, x3, x4. So you have to first take the products of all the propagators. So delta x1x or delta xx1, that is here, delta fxx1. Similarly, delta fxx2, delta fxx3 from this, and the delta fxx4 from here. So these are all the propagators. We have to have an integral over x. Okay, that has to be done at the very end. So that is here. There is one, so m is equal to 1. So basically 1 vertex. Okay, so that gives a factor of minus I lambda over 4 factorial. And the 1 over m factorial is trivial here because m is 1. And then you have to look for the combinatoric factors. Namely, the same diagram may actually represent many different terms. Okay, if the terms are all equal, you dump them into the same diagram. And here that comes because of the fact that the 4 lines that are coming out of these are all equivalent to each other, right? It doesn't matter if one connects to the first one or the second one or the third one and the fourth one, but they actually represent different terms in the expression. Okay? Because after all, we are applying this general formula, right? So after all, we are applying this general formula, right? This is where the diagrams came from. Okay? Here, if some of the x's are equal, you still have to include the separate contribution from those, right? Even though the terms themselves may be equal. So because of this, the same diagram may appear multiple times. Okay, and you have to count how many times it would have appeared. So here the counting, we went through it yesterday, but let me repeat again. Okay. So this number 4 comes from the fact that if you start from 1, okay, you can start counting from any where. Okay. But let's start counting here that how many ways this line can join. This line can join to any of the 4 lines that come out of this vertex over here. Okay. So that's 4 different ways. Okay, maybe I should go next to the other diagram. It's the same diagram. Okay, so I've just dropped the crosses just so that it doesn't clutter up the diagram. Okay. So this point can connect to any of these 4 lines. So that's the factor of 4. Okay. Given that, then 2 can connect to the 3 leftover lines. That's 3. Okay. And then 3 can connect to 2 leftover lines. That's 2. Okay. Then 4 has no choice. Okay. So this is the complete expression for the contribution from diagram A. Similarly, diagram B. First, we have to calculate look at the propagators. Okay. So delta f12, delta f x1, x2, delta f x3x. Okay, this point is again we are calling x. Delta f x3, delta f x4. See, inside delta f, it doesn't matter which order you put them, right? That we have discussed earlier. So delta f x x4. And this line, okay, this connects x to x. So that's delta f xx. You have the same minus I lambda over 4 factorial. And now the combinatoric factor, let's count. So 1 has no choice, it goes to 2. Okay, that's unique. 3 can go to any of the 4 lines coming out of this. That's factor of 4. And then 4 can connect to any 3 of the leftover lines. Okay, that's this factor of 3. And now you have 2 lines left over coming out of this vertex. They have to join each other, right? According to this diagram. So there is no further choice. You get a factor of 4 times 3. Is this counting clear so far? Any question?
Sir,
Yes, go ahead. Please.
I mean, can you please explicitly show what do you mean by 4 can connect to any of these lines?
Oh, 4 can connect to any of these lines?
Yeah.
Okay, so let's start with 1. Okay, so maybe I have to. Okay, so we had 1, 2, 3, 4, say. Okay. And here there are 4 lines coming out from here, right? Okay. So now the point is 1 has a line coming out. Okay. We know according to that diagram, that line has to go into one of the points at the center. Right? It has to connect to the point at the center. If 1 connected to 2, that's a different Feynman diagram. Okay. So now 1 can connect to either this one or this one. So let me draw those 4 possibilities. Okay, so this is 1. This is 1, 2, 3, 4. So this is the second possibility. So this is third. And this is the fourth one. So this is what I meant by saying that 1 can connect to any of the 4 lines.
Okay, got it.
Is that clear? Okay.
Yeah.
Once you have done this, once this possibility is realized, then 2 has only 3 choices, right?
Yeah.
Okay. And then once 2 is connected, 3 has only 2 choices, and so on. So that's the way you count. Okay. In terms of the original expression, right? We had a phi x to the 4 here, right? So if you think of this as phi x to the 4, right? Instead of saying phi x to the 4, you think of phi x, phi x, phi x, phi x, right? Then there is a delta f x1 x, right? But that x, the second x can be any of the 4 x's, right? It can come from any of the 4 phi's. And those are different terms in the original expression. And that's what we are counting here. Right? So the expression is the same, but there are different terms in the original expression which all give the same result. Okay? That's the factor of 4 we are counting. Is this okay?
Yes, it's fine.
Okay. Okay, any other question?
Sir?
Yes.
Sir, for example, in the second diagram, 1 could be connected to 3 also, and 1 could be connected to 4. We are not taking that diagrams into account.
Yeah.
The,
So those
the expression would be different, but that expression we are not taking into account.
No, we have to. So this is what I have said here, right? That below this line, right, that there are 6 diagrams of this kind.
Okay.
Okay. But I have not, those are not part of the combinatoric factors.
Yes.
Because you have to write separate expression.
Yes.
Yeah. So you have to certainly take into account. So the actual expression will have this plus 6 terms like this, and then 3 terms like this.
Yes. Okay.
Okay. So this is very important, right? You can't just draw one diagram and then be done with it, right? You have to draw all possible connections. Is there, that would fill up the whole screen, right? So I have not tried to draw all the diagrams, but you have to keep in mind that you have to add all those terms in the final expression. Any other question? Okay. So similarly, I have given here the contribution from the diagram C, right? See here 1 has to connect to 2, right? No choice. 3 has to connect to 4. That's what the diagram says. From here 4 lines are coming out. So let's take any one of them that can connect to any of the other 3 lines that are coming out of the same vertex. So that's a factor of 3. So once that connection has been made, we are just left with 2 lines which have to connect to each other, right? So they have no choice. So this corresponds to a combinatoric factor of 3. Okay, and that's what I have written here. But again, we should keep in mind that there are actually 3 diagrams which are obtained by inequivalent permutation of 1, 2, 3, 4. So there can be 1, 3, 2, 4 or 1, 4, 2, 3. Okay, those are separate expressions. So you have to add them separately. Okay, are there questions? So now I'll try to demonstrate how you can check, how you can be sure that you have drawn all the diagrams and you have got all the combinatoric factors. So the way to do that is that you calculate the total combinatoric factor of all the diagrams. Okay, sum over combinatoric factor of all the diagrams. So this gives you the total number of terms that you are manipulating. Okay, whose sum you are just organizing into these diagrams. So let's do that counting. So this number is 4 times 3 times 2, that's 24. Okay, so that's 24 over here. Here you have 4 times 3, so 12 is the combinatoric factor. But there are 6 diagrams. Okay? Each has combinatoric factor of 12. So that's 6 times 12, right? Total combinatoric factor from this class of diagrams is 12 times 6. And here the combinatoric factor is 3. And the total number of diagrams is 3, so that's 3 times 3. And if you add up these numbers, you get 105. Now you can ask, what should you have gotten? Okay. So the way you can see what you should have gotten is because the starting point, right? How many phi's we had to begin with? 1, 2, 3, 4 from here, and 4 phi's from here. So we started with 8 phi's, and you could have connected these 8 phi's in different ways. The total number of such possible connections we had calculated earlier. That was given by 2k factorial over 2 to the k times k factorial, right? Where 2k is the total number of phi's that you start with. This formula you remember? Okay, this formula is, let me go back here. Yeah, so this formula, okay, here n is k. This formula is the number of terms that we have here. Okay, we counted how many terms we will have in this sum. Okay, and if 2n is 8, then that number is 7 times 5 times 3. Okay, which is also 8 factorial over 2 to the 4 times 4 factorial. So this number you can calculate, and you say that indeed it's 105, and this gives you confidence that you have actually counted the you have included all the diagrams, right? Because if you didn't include all the diagrams, this number would be less than this. Is this point clear? Okay, so if there are no questions, I'll proceed. So this is what I have said here for general consistency check. That if we consider the collection of Feynman diagrams with n external points and m internal points, then the total number of phi's that you are starting with is n plus 4m. Right? Each external point gives you 1 phi each, and each internal point gives you 4 phi's each. Okay, this of course depends on the kind of interaction you are considering. Here you are considering phi to the 4, that's why it's 4m. So 2k is 4n plus 4m. These are the number of phi's that you start with. So the sum of all the combinatoric factors of all the Feynman diagrams will be given by this ratio over here. Okay, so this is something you should keep in mind. So the similar analysis can also be done for the denominator, okay, which is we had called earlier N1, N2. So here, as we have already said, the leading term is 1, right? That term is 1 because in this expansion, as you can see, it starts from m equal to 0, that term is just 1. And to order lambda, if you want to calculate, that's this Feynman diagram. In fact, there is a single unique Feynman diagram. Okay. And you can calculate this. Okay. Minus I lambda over 4 factorial, of course, is there. Okay, because of the single vortex. Okay. There's an integral over x as usual. And we have two propagators, each of which is delta f xx. Right? It starts from x and goes back to x. So delta f xx times delta f xx. What about the combinatoric factors? Combinatoric factor is 3 because out of the 4, the first one can connect to any of the other 3. That's 3. And then the second one then has no choice, but it has to connect to whatever is left. So that's the combinatoric factor here. So this is the expression for this diagram. So to order lambda, the denominator will be given by 1 minus this, or 1 plus this with a minus sign. So these diagrams we'll typically call bubble diagrams. Okay, these are bubbles. Okay, these have no external lines, and the denominator we say is 1 plus sum over bubbles. Are there questions?
Sir,
Yes.
in this case, there will not be any other inequivalent diagrams, right? Like in the other previous case, you have said that there will be
Yeah. So in this case, there is another inequivalent diagram. Yes.
Yeah. Okay.
Okay.
Thank
And
you.
you can check the counting again, right?
Yeah.
Here 2k is 4, right?
Okay. Okay.
Okay. And if you do the counting, you will find an answer 3. For 4, there are 3 independent terms, and that 3 matches this 3.
Okay. Thank you, sir.
Okay, so that's the way you can check this also. Any other question? Okay, now we are going to discuss an important result, which in fact makes life simpler, okay, in actual calculation. And the claim that we'll make now is that the numerator can be expressed as sum of diagrams without bubbles times 1 plus sum over bubbles. So why is this important? Let's suppose this is true. Okay, we'll check if this is true or not, but suppose this is true. In that case, the ratio of numerator to denominator is just a sum of diagrams without bubbles. So this says that if you want to calculate this ratio, which is an important thing because that's what gives the time ordered product of operators, effective expression of the time ordered product of operators, then you don't have to worry about the denominator at all. We simply sum of our diagrams, but ignore all bubbles. Which means that in this case, here, we'll forget about the denominator altogether. And while calculating the numerator, we'll include this diagram and this diagram, okay, but not this diagram. Okay, because this diagram has a bubble sitting here. Is this statement clear? So the claim again is that the effect of dividing by the denominator, which is 1 plus sum over bubbles, is to simply calculate the numerator but ignore all diagrams which has bubbles. Okay, like this one. Are there questions? Okay, so what we'll do now is to try to give a proof of this claim. Okay, how we get this. Okay, so to do that, let's start by analyzing the structure of the diagrams in the numerator. So each diagram in the numerator can be classified into one of the two classes. Either it's a diagram without a bubble, or it's a diagram without a bubble times a bubble diagram. Now this times is a formal statement at this stage. Times just simply means that you can think of this as a diagram without bubble, and then separately there's a bubble sitting. Okay, I'm not claiming at this stage that the expression is actually this product. Okay, then of course you'll be done, right? That'll be nothing to prove. This is what you want to prove. But at least at the level of the diagrams, like this one, we can think of this formally as this which has no bubble, and then the bubble. So at the level of diagrams, okay, without worrying about whether the factors are correct, we see that indeed the numerator can be thought of as a sum of a diagram without bubble, and then 1 plus sum over bubbles. Because in this product, whatever term appears in this product, right, is a diagram in the numerator, and vice versa. Given any diagram for the numerator, right, you can always identify one part which has no bubble, and then the rest you can think of as some bubble. Okay, so at the level of diagrams, this is indeed true. Okay. What you have to examine is whether it's also true at the level of actual expression for the diagram. Is this clear? No questions?
There can't be any terms which do not appear in the second summation but appears in the first summation.
In the second
like,
summation,
means some if we look at sum of diagrams without bubble plus sum of diagrams without bubble times sum over bubbles.
yes.
So there cannot be any term which is like appears in the first sum but does not appear in the second sum. Means yes.
You have any example?
So if you can go to the first that 3 pictures.
Yes. Okay. 3 pictures here. Yes.
Yes. So can we see that here? Because only the third.
Well, the third one has a bubble, right? This one doesn't have a bubble, so this is without bubble. But now you can also add a bubble, right? That's a higher order diagram. That is also an allowed diagram in the numerator. See, order lambda square, right? There's a diagram. Okay, maybe I'll draw it here. Okay. So this diagram doesn't have a bubble, right? But we can also consider this diagram. Okay, so this is also an allowed diagram in the numerator, right? So this is a part of diagram without bubble, and this is part of the 1 plus sum over bubbles. Is this clear? Okay, maybe let me try to do.
For this, do we have to go for higher order lambdas?
Yes, you have to go to higher order lambdas, right? So this statement is not order by order in lambda. Okay, so the point is that we have, you think of this plus this plus various things. Okay, you can have let's see if I did things correctly. All of these, times 1 plus bubble plus maybe 2 bubbles plus all of these, right? Okay, so this structure, if you take the product of any two, okay, that's also an allowed diagram in the numerator. Right? That's all we are saying here. Is this point clear?
Sorry,
Yes,
sir.
sir.
Sir,
Yes.
yeah, the third diagram in above expression is not allowed, I think, because the first vertex contains 5 lines.
Yes, okay. So somewhere something has gone wrong. Right? So some other vertex must be, oh, this is 5-point function you have drawn. So let's erase one of these. Okay, just 1 minute. So it's this one.
And
This is okay?
the combinatorial factors in the numerator and denominator exactly be the same.
Oh, no, that's what you have to check. Okay. So at this stage, I have not made a claim that combinatoric factors will be the same. This is something you have to prove.
Okay.
But at the level of the diagrams, right?
Hmm.
This should be clear.
Yes.
Okay, Sayan, is it clear? Is there confusion still?
No, it's fine.
So what we are saying at this stage that you take this formal product, right? Sum over diagrams without bubbles, which is in the first bracket, and then 1 plus sum over bubbles. You pick any combination of the diagram from the first bracket and the second bracket. That's certainly an allowed diagram in the numerator. Right? That's all we are saying here. We have not made a claim that the expressions are the same.
Okay.
Okay, so our goal will be to prove that the actual expression for the numerator is given by the product of the diagrams, the individual factors. Okay, only then you can say that as an algebraic expression, these two factors. Okay, but at this level, we are saying simply as a diagram, there is a formal factorization.
Sir,
Yes.
so we have to prove that every term in the expression is given by some combination of this diagram.
Yes, which is true, right? You think of
No,
any
so-
diagram, right, that contributes to a numerator. You can always divide it into a part which has no bubble and a part which has bubble.
Okay.
Is that okay? Or
Yes. Yes.
any diagram that you can draw, right? I mean, you can isolate the bubbles from the rest. Right? Bubbles are the ones which do not connect to any external line, right? Rest is which
Yes.
connects to at least one external line.
Yes.
Any other question? Okay, if not, let me go back to the screen again.
Hello, sir.
Yes, go ahead, please.
So the term for when there is 2 bubbles, so that can come from different orders
Different
of
order.
lambda.
Yes. Yeah. So this.
So the summing over for each number of bubbles
Yes.
from the initial order calculation that we have done.
Yes.
Now all the orders are there, like it's an exact
Yeah. So this is an exact statement. But once you have an exact statement, you can expand both sides to any given order in lambda, and the results will match, right? If two expressions are equal for all lambda,
Yes.
then their expansions will also match. Is that
But
correct?
for for a particular order of lambda, there wouldn't have all of the bubbles. Like there will be a finite number of bubbles.
True. Yes.
Okay.
Right. But once we have gotten an identity that the numerator of a denominator is numerator without bubbles, then if you calculate numerator of a denominator and expand to a given order in lambda, that will be the same as numerator without bubbles expanded to that order in lambda. See, if f of lambda is the same as g of lambda, right? Then it better be the expansion of f of lambda is the same as expansion of g of lambda.
Yes, yes.
Right? So that's what we will be using.
Yes.
Okay. So now the question is, can we check these expressions, right? That they are actually the same as expressions, right? Formally, we see that on the numerator, you have a structure that looks like a diagram without bubble and a diagram with bubble. A diagram without bubble and a bubble. But what about the expressions? Now, it's clear from the structure that the propagators give the same contribution on both sides. Then the integral over x, right? The same number of integrals over x are on the left hand side and the right hand side. Okay? Because for every vertex, we have an integration. So whether you think of this as a product of two diagrams or the same diagram, okay, that x integral will be there anyway. So what we need to check, okay, are the other factors, okay, the combinatoric factors, the factors that come from this expansion and so on. Okay. So let me explain what I mean by this. So let's suppose that we have a diagram without bubble which has m insertions of 4-point vertex. And we have a bubble diagram which has k insertions of 4-point vertex. Now, when you think of this as really a diagram without bubble, then the factor that we will get is minus I lambda over 4 factorial to the m over m factorial times the combinatoric factors, which we'll be counting later. Okay. So this is a factor that will come if you have diagrams without bubble, okay, and which has m insertion of 4-point vertex. If you have a bubble diagram with k insertion of 4-point vertex, okay, then we get a factor of minus I lambda over 4 factorial to the k over k factorial. Okay. So which means that the right hand side, okay, that this product over here, okay, or here, this product, okay, in this product, you will get a factor of minus I lambda over 4 factorial to the power m over m factorial times minus I lambda over 4 factorial to the power k over k factorial. On the left hand side, all we will count is that we have m plus k interaction vertex. Because we will not count separately that there are m of these go into bubble and without bubble and k go with bubble, right? Our rules say that if you have m plus k interaction vertex, then the factor that you have is minus I lambda over 4 factorial to the power m plus k over m plus k factorial. And now you can see that these are not the same. These factors, of course, cancel. Minus I lambda over 4 factorial to the m times minus I lambda over 4 factorial to the k is indeed the same as this. But here you had 1 over m factorial times 1 over k factorial. Here you have a 1 over m plus k factorial. So this is same as what we will get from the right hand side, okay, namely this product. But there will be an extra factor, is m factorial k factorial over m plus k factorial. Is this point clear? Any question?
Why this extra factor? M factorial, k factorial, m.
Okay, because the right hand side has 1 over m factorial times 1 over k factorial, right? That is clear, right? If you count this as a diagram without bubble, it will have a 1 over m factorial because there are m vertices inside the diagram without bubble. Right?
Yeah.
Then if you consider this as a bubble diagram, right, which has k insertions of 4-point vertex, so that will have a 1 over k factorial.
Yes.
But on the left hand side, when you are considering this as a single diagram, right, then you have m plus k interaction vertex.
Yes.
So if you have m plus k interaction vertex, our instruction says that you should divide by m plus k factorial.
Mm.
So that's why this factor is not the same as the product of these. There is extra piece over here, right? 1 over m plus k factorial is 1 over m factorial times 1 over k factorial times this number. Is that clear? So what we
Yes.
are saying is the left hand side is not the same as right hand side, okay, for this particular term, but that this particular term on the left hand side has this extra factor compared to the term on the right hand side.
Okay.
Okay. So what we have missed so far, what I have not counted so far, are the combinatoric factors. Because besides this, of course, we also have to count the combinatoric factor for this diagram, and the combinatoric factor for this diagram, and the combinatoric factor for this diagram. And what we will try to argue now is that this factor that we are missing is exactly cancelled by the combinatoric factors. Okay, that the combinatoric factor of this is not the product of the combinatoric factors of these two, okay, but there's an extra piece, and that extra piece is going to cancel this. Are there questions? Okay, so let me then show this. So of course, generally counting combinatoric factors is difficult, right? But what we are asking here is, we don't even know what the diagram we are talking about, right? So you cannot really say what the combinatoric factor is. Okay? But what we are asking here is not actually the combinatoric factor, but the relative combinatoric factor between these two sides. Okay, so to compare this, we note that the numerator diagram has m plus k 4-point vertex. The other side, the right hand side, has a bubble which has k vertex and a diagram without bubble which has m vertex. So now, given this m plus k 4-point vertex, some of these form part of the bubble, some of these form part of the 4-point vertex. But that choice, of course, is ours, and irrespective of what the choice is, the expression is the same, right? It doesn't matter whether it is the first vertex that becomes part of the bubble, or the second vertex that becomes part of the bubble, or the third one that becomes part of the bubble. As long as k of these become part of the bubble, we have the bubble diagram. So the numerator diagram, that means the one which has the full set of diagrams, both bubbles and diagram without bubbles, that has an extra combinatoric factor compared to the product on the right hand side, and that is the factor that tells us in how many ways you can choose this k vertex that becomes part of the bubble out of this m plus k vertex that was there as part of the 4-point vertex, or part of the numerator diagram. So this factor is m plus k choose k, okay, and that's m plus k factorial over m factorial times k factorial. So this exactly cancels the missing factor that we had. Okay, remember that here the numerator factor had this factor missing, right? This numerator factor was given by this times the product. Now we say that the combinatoric factor of the numerator actually has m plus k choose k compared to the product of the other two. Okay, so we have this extra factor in the numerator, and that cancels this factor. And you can easily convince yourself the rest of the combinatoric factors are the same on the right hand side and the left hand side, because that simply measures the number of ways a diagram without bubble can be formed and the number of ways a bubble diagram can be formed. So we are dividing the calculation of the combinatoric factor into two parts. One is that in how many ways the original m plus k vertices can be distributed into part of the bubble and part of the diagram without bubble. After that, there is a very complicated calculation you have to do to figure out what is the combinatoric factor for the bubble and what is the combinatoric factor for the diagram without bubble. But that calculation is common in both diagrams. The extra work that is involved in calculating the numerator, okay, which is the total diagram, is in how many ways you can choose these k vertices that become part of the bubble out of m plus k. And that's what then establishes that indeed they are the product, okay? They are product not as formally at the level of the diagrams, but also as an expression. So this gives this result. The numerator is actual diagram without bubble times 1 plus sum over bubbles. Denominator, on the other hand, is 1 plus sum over bubbles. And that gives the result that this matrix element that you're trying to calculate is indeed sum over Feynman diagrams without bubbles. Is this clear?
Sir,
Yes, go ahead, please.
sir, you just said that if on the left hand side, we will choose the k vertex which are related, which are the bubble vertex
Yes.
out of m plus k vertex.
Yes.
And the remaining factors will be same on both sides.
Yes.
So does that mean that so the remaining factors will be, so this point is not clear to me. So how they will be same?
Because rest of the counting is the same, right? Okay, let me again withdraw. Okay, so let me draw this as an abstract drawing. Okay. Okay, let me call this the diagram without bubbles. Okay, and here you have bubble. Okay, there are m vertex from here, okay, and there are k here. Okay, now we had m plus k vertices to begin with. We choose k out of m plus k. Okay, that's this factor of m plus k choose k. After that, imagine that you are doing separate bubble calculation and this calculation, okay, or you are doing the combined calculation. The way you will calculate the combinatoric factor, okay, in this combined calculation, okay, will be that you will first calculate the combinatoric factor here, right? In how many ways these can connect, right? Given that these m vertices have been fixed. Okay? And then you will also calculate in how many ways things can connect here and take the product. Right? That's probability, right? Or that's the number of counting, right? How many ways you can do things here and how many ways you can do things here determines how many ways you can do things in total. So the only extra ingredient is that this has m vertex, this has k vertex. In the full diagram, you had m plus k vertices, and out of this m plus k, you have a choice of what you call the k, which of this m plus k we call k vertex here, and which of the m plus k we call m vertex here. The rest of the calculation you can see is the same, right? Because you will find out how many ways these connections can be made here, right? And how many ways connections can be made here. And the product of these will tell you in how many ways connections can be made in the full diagram.
Okay. Okay.
Is that clear?
Yes.
Okay. And you can also see this in explicit example. Let me stop this. Okay, this is of course a very simple example, but you can still see this. You see here, with the combinatoric factor came besides purely from here, right? Okay, because 1 could have to go to 3, 2 and 3 has to go to 4. So the combinatoric factor that you found from here is 3. And that's the same as the combinatoric factor of this. And it's not an accident because it's the same counting.
So the screen is not shared, I think.
Oh, screen is not shared. Oh, sorry. I'm sorry. Let me. Okay. Can you see it now?
Yes.
Okay. So what I was saying is that if you look at this diagram over here, right? Diagram C, which has a bubble. Okay, you counted the combinatoric factor of this diagram. Okay, but if you examine the combinatoric factor of this diagram actually came from this part, right? Because this part had no choice really. 1 had to go to 2, 3 had to go to 4, right? And the combinatoric factor of this part turned out to be 3. Okay. Now, when you actually do the calculation by divide by the denominator, you will actually ignore this diagram. Okay. And for that, you will have to use the fact that the combinatoric factor of this diagram is the product of the combinatoric factor of this diagram and the combinatoric factor of this diagram. And this is indeed true, you can see, because we also separately counted the combinatoric factor of this diagram, right? That's also 3. And it's not an accident that this 3 is the same as this 3. Okay? Because it had to be that it comes from the product, right? Product of what you count here and what you count here. Okay? With the proviso that if for example there is a vertex here, right, we could have exchanged the 2, right? That will give the factor of 2, and that's this m plus k choose k, right? That factor. Is this clear?
Yes.
I think it may become even clearer if you work out some examples, right? Take for example the product of this and this. Okay, you can do the calculation in two ways. First, you calculate the combinatoric factor of this, then you calculate the combinatoric factor of this, and then you calculate it as a whole diagram. Okay, combinatoric factor of the two things together, and you will find that you will get an extra factor of 2, okay, from this product, and that extra factor of 2 is precisely counting the fact that there are 2 vertices out of which you have to choose one, right? To become part of this, the other one will become part of this, and that's the extra factor of 2. In this case, that extra factor of 2 was not there because m plus k is 1, right? And k is 1. So it's 1 choose 1. That's 1. That's why you got exactly the same combinatoric factor between this and the diagram over here. Any other question? Okay, if not, I think I'll stop here. And so now I'll ask those who are not taking the course as registered students to sign off, and we'll continue with the meeting with the registered students. So I'll stop the recording also.